Okay, guys, I am going to go back to hybridization and do a really short video on hybridization and then sigma and pi bonds, because my last recording was flashing that I went way over time, so I went to pause it and then it just ended it. So you're missing some of this, not all of it. Watch the first recording for the energy. Go towards the end to look at the energy. So again, hybridization, so you can do your lab, because that's part of what you have to do with hybridization. And I'm going to go back to my little full screen here. When you look at hybridization, it is a way to make more bonds. Okay, so hybridizing allows the orbitals to reshape. So you can make more bonds. More bonds than you normally would. So that's carbon's a big one, right? If you're looking at carbon, carbon can take 4 electrons, but the place to be able to share electrons, bringing electrons to the bond, both from the carbon and from another atom, really comes from the combination of these 2 orbitals. So what carbon does for its even natural, like if you draw carbon's Lewis dot like this as an atom, it is acceptable. But normally we draw it this way, but you can draw it this way and get credit for it, because when carbon does go to bond, it does do this thing called promoting an electron. It takes an electron from the s orbital and pumps it up in energy, and then the orbitals go through this reshaping. Okay, so if we look down below right here, this is like saying, okay, in space, if you put this on, your 3-dimensional coordinate, you have s in the middle, and then you have your p's on each thing. And they're saying this reshapes, and when you reshape it, you end up with this 3-dimensional type space. So now the p's aren't on the axes anymore of your 3-dimensional space. They're more into the plane and go below the plane, so they hang out in different regions. So it's been reshaped. Okay, so this reshaping allows for more atoms to attach and share the space of electron density. And that's why we say that these 2 orbitals come together. They're on the same energy level, but they come together and they reshape. And we now have 4 spaces, right? Here's 1, here's 1, here's 1, here's 1. And now we can make 4 bonds. Before, really, we had 2 places to share in this open space, so we weren't going to make as many bonds with the carbon. Can we just do other types of hybridization? Yes. In carbon, when you only need to make 1 sharing on each end of the carbon, we do this thing called sp hybridization. So it's little, you end up with this weird, and I don't know if I can do it. There's this little orbital that looks like this. So you share on the s and you share on the p, and the rest of the p's are the same. They come out like this and then go down. So it's only 1 s and 1 p that hybridize to make the bond. These are all of them hybridizing, right? So hybridization is the changing the shape of the orbitals, moving electrons around so you can make as many shared regions as necessary to make the compound. Now, what do you need to know? Do you need to know the shapes and redraw the shapes? No. What you need to know is the type of hybridization that happens at the atom they designate. And you might say, how the heck do you figure that out? Oh, it's easy. Okay, we're going to keep it easy. We're going to look at your domain. Okay, if we are in a 2 domain, so when we do the lab, we're going to see that this is a 2 domain. And when we look at the hybridization on that carbon, it's an sp hybridization. So you count bonding domains. There's an s and a p. So I have sp domain or sp hybridization. Notice these have superscripts of 1. It's understood to be 1. If I add the 1's together, 1 plus 1, it equals 2, and I'm in the second domain. If I look at carbon in a tetrahedral, it doesn't matter what's attached to the outside. This is an S, P, P, P. So I have sp3. And if you do this on your drawing, you will figure out the correct hybridization. Some people can say, oh, 4 domains. So if it's 4 domains, this is a 1 plus 3 equals 4. So if I add those two up, these two are equal, so I had to have an sp3. I tell people, go to your drawing and look at your domains and label your domains. Start with S and then do P, P, P. If you're in a bigger one, like xenon with 4 things off of it and lone pairs, okay, you can still do this. I'm going to change the color of my pen just so you can see me labeling it. Here, it doesn't matter where you start. S, P, P, P. Now we run out. We don't have any more P's to put in there. There's only 3 P orbitals. So now we go D, D, D. Oh, I have S, P3, D2. If I add these up, right, 1 plus 3 plus 2, that equals 6. I'm in the 6th domain when I have that. And that is how you try it, determine your hybridization. You can even do this on oxygen. They'll ask you about oxygen. They'll ask you about carbon in the middle of a big compound. So if I have oxygen and it's double bonded to a carbon, and I'm sorry I'm rewriting over things, right? And oxygen has 2 lone pairs out here. And you would know that by doing your Lewis dot, because oxygen likes to either make a double bond or a single bond. So you can see oxygen like that. You'll also see oxygen like this, right? This is carbon, and then there's more coming out here. When you see this, and they say, what is oxygen's hybridization? It's sp, P. This is sp2. Over here, though, it's sp, P, P. Each one of those is a domain, so that's sp3, which makes sense, though, because if you go back all the way to where we made that wonderful little oxygen, sorry, I'm flipping too fast, in this one right here, on the bottom, where you have water, oxygen in the middle, 2 things bounded off of it, you have an sp-p-p. You are in the 4th domain. In the 4th domain, and that's why these aren't filled in, because to fill these little things in, it's kind of like this is sp3, hybridization. Okay? So that's hybridization. Again, you can do that anywhere. If I have carbon in the middle of an organic structure with that, like what I drew with the oxygen, if I want to know what carbon's hybridization is, spp. Well, that's also an sp3 because it's 3 domains. If you look at that, that's 3 domains. All bonding. All bonding, 3 domains. If we go back up above, that's trigonal planar. For that carbon, this one right there, right? The bonding angle between here to here would be 120. And they'll do this in AP. They'll give you this huge structure. They'll pick a carbon and they'll say, well, what's its hybridization? What's its shape? What's the bond angle? They could ask you any 3 or all 3. And you have to think, oh, I got to go back to Lewis dot. I got to count bonding domains. Once I know my bonding domains and my unbonding material, then I can figure out my shape. The other thing I'm going to try to get through quickly here is S and P orbitals. So go back, guys, to the long video towards the end to watch the explanation about these energy diagrams. You do need to know how to do those energy diagrams. Again, you guys are AP, so I'm going to say to you, you go do this, you go find it there. If you choose not to and you're like, I'm going to skip it, that also means that you won't get the points when you're asked the questions. Okay, this is up to you. Now I'm going to force feed you this. All right, sigma and pi bonds are types of descriptions of what happens to the electrons in the bonds. Like, are they in along the axes between the 2 elements, or they are above and below floating in space, but shared between the 2 elements? So when we look at a sigma bond, that sigma bond is considered a single bond. So think SS, sigma, single. right? Sigma, single. I'm going to highlight for you. Single bonds are sigma, SS, SS, sigma, single. Okay? That means that you're looking at the axes between the two and that they are shared along that axis. They overlap on an axis and they're connected in a single bond. That's the sharing. So, like I said, axis between the nuclei. So any single bond, this is a single, therefore sigma. I mean, sigma's Greek. That's the lowercase sigma. You know the uppercase sigma as a sum. You probably don't even know this. This thing right here was a sum. That's sigma, capital Greek letter. This is lower case Greek letter. Okay. All of these, every single one of these is single. So in this in this molecule, I have 1, 2, 3, 4, 5, 6, 7 sigma bonds. Now, in a molecule that has a double bond in it, and I'm going to write this off to the side. I think pen shows up pretty good on the black. Okay, I have carbon double bonded to carbon. We have a hydrogen, and then it's like this because of the stereochemistry, right? It's 120 degrees, so you take your circle and divide it into threes because this is an sp3, right? That's an sp3 right there. So that's 120 degrees between the angles. This is why it's drawn this way. And some people say when we go to draw organic structures at the end of the year, does it matter if I put the H above or to the side? No, Regents doesn't care. Even if you were doing organic for AP and they assume you already have organic, like the small intro that you get in Regents, we do it as we discuss through the year. So essentially, I'm showing you organic here because it's carbon and hydrogen. AP doesn't get that particular. When you go on and you're doing collegiate material at college, they'll say, oh man, you shouldn't be drawing it. They're not going to accept this type of structure because they're going to tell you, you should know that between here to here, you need 120 degrees. That isn't drawn 120, that's drawn 90. That's wrong. Okay. Now, no, not for us right now. When you draw your Lewis dots on a bonding test, yes, but not for what Regents will ask for organic and not really for AP. But I digress. Here's my double bond. So in the double bond, in this bond right here, there's two things going on. You have bonding along the axis, which is a sigma, but then you have the p orbitals. And when you have a double bond, one set of the p's share the electrons move back and forth between the two atoms. So in a double bond, we say a double bond has one sigma and one pi. If I add another bond into that, so I'm going to take this and now I'm going to make this a triple bond. So now I have a different amount of H's and everything, which also changes the stereochemistry. Stereochemistry means the geometry and whether you have what's called rotation of light through the bond. So here's a triple bond. So I have a sigma where they overlap in between. And then I have the pi's that go in, this way. And now here's the hard part. And I'm going to change my color. I'll do a nice bright orange because you can see that. No, it didn't change my color. You pulled it off. Change it. This goes out at you and then it goes back into the computer and comes out and goes back. And then there's another one there to make it a pi. So when you have a triple, you get one sigma and two pi's when you count types of bonds. And that's all you really need to know about sigmas and pi's right now. If we have time, I will go through this stuff on the bottom, which is molecular orbital theory. This is very much into the quantum that goes on with a bond. AP took it out. They don't ask you about this. The bonding, anti-bonding, like, matter, antimatter, it's areas of space really used in conduction where you where you make an electron go to an antibonding orbital with energy. So then within something that's kind of rigid, you make the electron move so it's no longer fixed, and then you can conduct, and that's how semiconductors work. But I'm not going to get into that now. If we have time, we'll do it. I save it because I reassess this as we get closer to the AP. So you have the notes. You're going to hold on to your notes. You're not going to throw your note packet away. If I decide close to the AP we have the time to go through it, I'll show you. They don't test you on it. Most of the times I'll say, it's more important that we practice AP test questions than for you to know bonding and antibonding orbitals. It actually has a nice link to our bond order, because if you do go through and you say, I'm going to fill in the notes anyway, it tells you how to fill them in and how to get through and how to come up with your bonding order. And you will see a lot of correlation between our resonance structures and bonding order. But I'm leaving that up to you.